Hi, all. Thank you for your interest. Today, I will introduce my work on PUS, partial update solver, which is a faster solving algorithm for inclusion-based point analysis. For those who might not be very familiar with point analysis, pointer or alias analysis is a fundamental technique used in an enormous amount of static analyzer, such as value flow analysis, deep bug detectors. It is also the prerequisite of many compiler optimizations. On one hand, having a precise point analysis can usually dramatically eliminate the false positive reported by the static analyzer and or strengthen the optimization performed by the compiler to generate more efficient code. On the other hand, a precise point analysis is infamous for its poor scalability. At a high level, point analysis is a static analysis technique that statically computes a set of objects that could be pointed by a pointer during runtime, which is referred as the point-to set. It is essential to analyze program language with pointers or references by computing information on how different pointer can access the same or different pieces of memory. It also helps to compute a complete call graph in presence of indirect function calls, such as function pointers in C and the virtual functions in C++ and Java. So inclusion-based point analysis especially computes the point-to set information by abstracting different statements into inclusive functions as shown in the table. For example, as in the second row of the table, then the value of V2 is assigned to V1. The point-to set of V1 should include the point-to set of V2. And then the goal of the point analysis or the solving algorithm is to compute a point-to set for every pointers in the program such that all the constraints are satisfied. This computation is normally performed on a constraint graph, which use edges to represent the inclusive constraints between different variables. Take this slide as the example. The point-to set of A and B are first computed after analyzing the highlighted two statements according to the adjust taken rules by inserting C to the point-to set of A and A into the point-to set of B. Then the assignment constraint is processed, and according to the rule, the point-to set of D should include the point-to set of A. Thus, C is inserted into the point set of D as well. Then the store statement is processed such that an edge between B and C is inserted to represent the inclusive relation between B and C. Then by processing the load statement, an edge between C and A is inserted to represent the inclusive relation between point-to sets of A and C. Note that the algorithm will not terminate at the current stage, as the constraint between A and D are still not satisfied because the point-to set of D does not include the point-to set of A while there's an edge between A and D. The algorithm is then repeated for several times until reaching the minimum fixed point and all the constraints are satisfied. The solving algorithm seems to be simple. However, the point analysis, especially applying point analysis on the whole program, are known to be unscalable. As a result, most commodity software either has to avoid the use of point analysis by applying inaccurate heuristics, or it has to spend hours to analyze non-trivial programs. There are currently two state-of-the-art solving algorithm point analysis. They are namely wave and deep propagation. At a high level, wave propagation algorithm first topologically sort the entire constraint graph and then propagates the point-to information in topological order, and they do it repeatedly until reaching the fixed point. The deep propagation algorithm first do one round of wave propagation and then propagates the point to information in a DFS manner, depth first search manner on constant graph. So both algorithms actually take the constant graph as a whole, and they will process the entire graph at each iteration. While we observe that at each iteration in the solving process, only a very small subset of the constant graph are actually affected by the update from the previous iteration and are required to be processed in the current iteration. Thus, the points to information propagation only need to be done on a small effective subgraph instead of the entire constant graph. At a high level, instead of processing the whole graph at each iteration as existing algorithm on the left-hand side, partial update solver first computes an effective subgraph. It can actually done simultaneously when you're trying to topologically sort the graph at each iteration, and it only propagates the point to information on the small subgraph. Take this example. When compared to wave propagation, partial update solver only process node 2, 5, and 8, as they are the only nodes that are affected by the update from the previous iteration, which is inserting B into the pointer set of node 2, while the wave propagation will have to re-topological sort the entire graph. When compared to the deep propagation, PUS avoids redundant computation as it propagates point to information in the optimal order on the effective subgraph. Well, deep propagation will have to process the flow between V1 to Vn twice. Of course, this is a very high-level introduction of the algorithm, but it shows the essence of the PUS. It should be noted that we also formally prove the correctness of the algorithm, which means that PUS is guaranteed to yield exactly the same result as wave and deep propagation. So we evaluated partial update solver on a large benchmark, including projects with more than 1 million lines of code. And the table shows the size of the effective subgraph only contains less than 3% of nodes and 2% of edges of the entire graph on average, which means that most of computation, redundant computation, can be avoided. And this slide shows the whole lifetime of the size of the effective subgraph. And when analyzing one of the benchmarks, as you can see, the size of the effective subgraph always contains less than 10% of node and edges of the entire program during the entire solving phases. So for the performance, when applying partial update solver to solve context-insensitive point analysis, it shows it is more than 3 times faster than wave propagation and more than 2 times faster than deep propagation on average. Especially, it can have more than 7 times speed up on memcached. On the other hand, when you're applying partial update solver to solve context-sensitive point analysis, it yields even more promising result because PUS is more than 7 times faster than wave propagation and almost 9 times faster than deep propagation on average. This is because context-sensitive point analysis always yields a more sparse constant graph, as it will use multiple nodes and edges to present the same variable under different contexts, which means PUS, the effective subgraph are even smaller when compared to the context-insensitive ones. So we also noticed that despite of the huge improvement, partial update solver is still not good enough to process large programs on commodity hardware. and they easily run out of memory when analyze 1 million line projects. And thank you all. This is all my presentation. And well, I'm looking forward to the live discussion we'll have during the conference.